The data science world is definitely changing rapidly. It's being pushed forward by constant innovation, but also this huge demand, right?
Wow.
Businesses need people who can actually turn data into action. And as companies rely more and more on data for decisions, we're seeing these roles become much more specific, more specialized. Your sources really highlight 4 roles that seem particularly crucial for where things are heading. So that's where we'll focus today's deep dive.
Who's wrangling all the data needed to feed them? That sounds like a huge job in itself.
That's exactly where the data engineer fits in. Think of them as the architects, the custodians of an organization's data infrastructure. They build and maintain the systems for collecting data, storing it, processing it, and crucially, making it accessible. They basically build the data highways and the plumbing. You could say they're the absolute backbone supporting any data-driven company.
Right. So what are their main tasks on a typical day?
It really boils down to data management. They're designing, building, and maintaining robust databases, data architectures, and especially data pipelines. These pipelines are critical for pulling in large amounts of raw data from all sorts of sources and then processing it. A huge part of their job is getting that data ready for data scientists and analysts, making sure it's clean, accurate, usable. This involves everything from spotting inconsistencies to building automated workflows to clean and reshape the data.
So a lot of behind-the-scenes work to make the data useful.
A ton. You'll see them heavily involved in ETL extract, transform, load, or sometimes ELT processes, extracting data, transforming it into the right format, loading it into data warehouses or other systems. They have to merge data from different places, check it, parse it, clean it. There's a lot of coding involved, often focused on making things efficient and scalable. They build optimized data stores for analysis and set up ways to serve that data reliably.
Do they mostly work alone, or is it collaborative?
Oh, definitely collaborative. It has to be. They work very closely with business analysts, IT teams, software developers, and especially data scientists to really understand what data is needed and then build the right infrastructure to deliver it effectively.
What are some of the biggest challenges they face? The main headaches?
Just ensuring the data quality is consistently high, accurate, clean, ready to use, that's a constant battle. And handling the sheer volume of data, often coming in fast from many different places, and processing it quickly and reliably, that's immense pressure. Dealing with messy, inconsistent data is just part of the daily grind.
I've heard data engineers can specialize a bit too, is that right?
Yes, your sources mention that. You have generalists who kind of do everything data related. Then there are those who focus heavily on the pipelines managing the flow of data, and others who are more database centric, really specializing in designing and managing complex database systems.
Okay, let's talk tools. What technical skills are absolutely essential for a data engineer?
Python and SQL. Those are the absolute foundations. Your sources say they show up in, 70% and 69% of job postings, respectively? So yeah, critical. Other languages like Java, Scala, sometimes Go or C#, they pop up too, often for specific performance needs or system integrations. And deep knowledge of databases is a must. Both relational ones like PostgreSQL or MySQL, and NoSQL databases like MongoDB or Cassandra, plus expertise in data warehousing platforms Snowflake, Redshift, BigQuery are the big names there.
And for building those crucial pipelines you mentioned.
Yeah, they need to be proficient with ETL or ELT tools. These automate moving and transforming data. Your sources list things like Apache Airflow for managing the workflows, dbt Cloud for the transformation logic, and various cloud-native services like Azure Data Factory. And for really large data sets, knowing big data tools like Apache Spark and Kafka for processing is pretty much essential.
Cloud skills seem vital across the board. What's the focus for data engineers there?
Huge. Cloud expertise is absolutely huge. They need to be very familiar with the services on the major platforms, AWS, Azure, Google Cloud, especially the ones for data storage, processing, and management. AWS seems to have the edge in mentions and job postings according to your sources, but Azure is right behind it.
You mentioned DevOps skills earlier. That sounds interesting for a data role. How does that fit in?
Yeah, this is a really significant trend, I think. We're seeing more and more expectation that data engineers possess skills from the software development world. Things like CI/CD continuous integration, continuous deployment, and tools like Docker for containerization, Kubernetes for orchestration. It's not just a nice to have anymore, it reflects this key insight. Data pipelines are being treated like critical software products. They need version control, automated testing, reliable deployment, all the best practices from software engineering.
Gotcha. Are there other important skills besides the core coding and infrastructure stuff?
Definitely. Data modeling, designing how data is structured efficiently. Data governance and security are becoming increasingly critical, protecting data, ensuring compliance with rules like GDPR. API and integration skills are needed to connect to various data sources. And interestingly, your sources suggest even data visualization tools like Tableau or Power BI are showing up more. It implies data engineers need to understand how the end users, the analysts, and business folks are actually going to consume the data they provide. The path seems pretty standard. Starting maybe as a trainee or junior, moving to a mid-level role, then senior. After that, it can lead to leadership goals like manager of data engineering or deep technical expert roles like data architect. It's also quite common for people to move into data engineering from related fields like software engineering or business intelligence.
What about the job market overall? Still strong?
Yeah, strong and stable seems to be the message. Growth projections are consistently solid. It's a foundational role. Thousands of jobs are opening up each year. It's in high demand because every data initiative relies on them. So, the key insights for data engineering. One is that skills-first hiring trend. Practical ability with the tools often counts for a lot, which is great news if you're changing careers. And second, that growing need for DevOps skills. It really highlights how data infrastructure is maturing, adopting serious software engineering discipline to build reliable, scalable platforms. That blurring of lines means being adaptable is really key. Which really brings us to a final thought, a question for you listening. Given this rapid evolution and all these diverse paths and specializations opening up in data science, how do you decide? Which qualification method, which area of focus feels like the right one for you as you look towards your future in this data-driven world? Welcome to the deep dive. Ever find yourself looking at just a massive amount of data, maybe sales numbers, customer notes, sensor data, and just wondering, how do I find the key thing? How do you cut through all that noise to see what's actually going on before you even start thinking about complicated models? Well, that's what we're digging into today. Exploratory data analysis, or EDA. Think of it like a decoder ring for data, a way to let the data itself tell you its secrets.
It really is. EDA isn't just another step. It's more like the fundamental way you get to grips with a data set. Understand its shape, spot the patterns, find the weird bits, the anomalies.
Yeah, the detective work.
Exactly. That's where it starts. It lays the foundation for, everything else.
Okay, let's unpack this a bit then. So, EDA. It's like a systematic way to poke around in data sets, right? Summarize them, often using visuals.
Precisely.
Yeah.
The main goal is to figure out what the data is actually saying on its own terms. It's not about rigidly testing some hypothesis you already had.
So you let the data lead the way without sort of prejudging it.
That's the core idea. And it's got history. This approach, this sort of flexible, curious attitude, it came from John Tukey, a brilliant American mathematician back in the 70s.
Tukey, right. I've heard the name.
Yeah. He felt statistics was maybe too focused on testing hypotheses. He argued we should use data to suggest hypotheses in the first place. It really enriched the whole discovery part of analysis.
So it's more about the mindset being flexible, inquisitive.
That's a great way to put it. It's an attitude.
And here's something really interesting, Heather, again. It's not just a one-off check.
Oh, absolutely not. It's a cycle. You analyze, you visualize, maybe you transform the data a bit, and you analyze again to see what else pops out.
Like you might be looking at sales data, just exploring, and suddenly you see these clear seasonal spikes you never noticed before.
Exactly. And that one insight could send you down a totally new investigation, maybe about why those spikes happen. Deeper insight.
Right. It's like peeling an onion.
And if you connect that to the, let's say, the practical side, EDA is basically your first line of defense. Risk management strategy, really.
How so?
Well, it's absolutely critical for catching things early. Glaring errors, missing information, duplicates, those weird outliers that don't fit.
The stuff that can really mess things up later if you don't catch it.
Precisely. Without that cleanup, any models you build later might be biased, they might not work well, or worse, they could lead you to completely wrong conclusions.
The classic garbage in, garbage out problem.
You got it. EDA stops that and makes sure your foundation is solid, like checking the ground before you build a house.
Makes sense. So when people actually do EDA, I keep hearing Python is the go-to tool. Why is that? What makes it the main engine here?
Yeah, Python's huge in this space.
Yeah.
Its ease of use is a big part, but it's also the ecosystem. Libraries like Pandas are fantastic for data handling.
Like getting a quick summary.
Exactly. Things like df.info to see data types and missing values, or df.describe for basic stats, instant snapshots. And then for the visual side, you've got Seaborn and Matplotlib. You can create a heat map to quickly see correlations, or a pair plot to visualize relationships between many variables at once. It's just very powerful and flexible.
So the tools make that investigative process much faster and easier.
Definitely. But beyond the tools, the real magic is how useful EDA is everywhere. I mean,
What?
across so many different industries.
Any cool examples spring to mind?
Oh, sure. Think about Walmart. They use ED constantly. Analyzing customer buying habits helps them stock shelves better, obviously. But they also use it for things like predicting delivery times more accurately, or even figuring out the best box size to use for shipping to cut down waste, all from exploring their data.
Wow, okay. That's pretty sophisticated stuff from just exploring data.
It is. Or there was a case with a fruit supplier. They kept getting complaints about overripe fruit. So they used EDA. They plotted complaint data against things like delivery routes, storage times, temperatures.
And they found a pattern.
They did. They pinpointed when and where the fruit was most likely to become overripe. This led them to change their picking, packing, and storage methods. And the result? A massive 64% drop in complaints.
64%, just from looking at the data they already had?
Just from exploring it properly, it shows how powerful simply looking can be.
It really does. So it sounds like being good at EDA isn't just a bonus for data scientists, it's table stakes, right?
Foundational.
Absolutely fundamental. It directly impacts your ability to make good data-driven decisions and really unlock what's inside any data set. So wrapping this up then, what's the big takeaway for you listening? EDA basically takes that raw, maybe messy data and turns it into something you truly understand, a resource. And that understanding lets you build better models, find smarter solutions, all because you listen to the data first.
Which leads to maybe a final thought to chew on. Think about the data you encounter. What patterns, what stories might be hiding there, just waiting for someone curious enough to look.
That ability, Tukey talked about understanding data before jumping to conclusions. It's just as crucial now as it was back then, maybe even more so.
Welcome to the deep dive. Today we're really digging into something crucial, maybe often skipped over, but, well, fundamental for data science and machine learning success. We're talking about the real importance of data shape.
Right, it's like the blueprint for your data set.
Exactly, the initial blueprint. And if you get that wrong, you're building on, pretty shaky ground. And here's something stark. Solid data validation, getting that shape right. It's not just like good hygiene, it can seriously boost predictive accuracy. We're talking up to 30%.
That's significant. And think about the flip side, too.
Yeah, what's really fascinating, maybe a bit shocking, is that apparently up to 85% of errors in AI development, they trace right back to poorly curated inputs.
85%. Wow. It really is that garbage in, garbage out principle, isn't it? Like trying to build a skyscraper on sand, as you said.
Totally. So, okay, knowing it's crucial is one thing, but how do we actually start to read that blueprint? What are the first signals? Like mean, median, mode, what do they tell us?
Okay, so mean, median, mode.
Yeah.
We're kind of our first look at the data center. But honestly, for what we're talking about, the real story is often in how they differ.
How they differ, okay.
Yeah. That's your standard average, right? But it's super sensitive to extreme values, outliers.
Right, like the classic example of income data. A few billionaires walk in.
Exactly. And suddenly the average is meaningless for most people. That's where the median shines. It's just the middle value when you line everything up. So it stands firm against those outliers. Gives you a much truer picture for skewed stuff, like income.
Okay, so median's more robust for skewed data. What about mode?
Mode's simpler, just the most frequent value. Really invaluable when you're looking at categorical data, like most popular product killer or something.
Got it.
But here's where it gets really interesting. By seeing how these three measures relate, just comparing them, you can immediately get clues about the data's shape. Things like skewness, is it lopsided? Kurtosis, how pointy or flat is the peak? Or even multimodality does it have, like multiple humps?
And how do you see that visually?
Histograms are key. Box plots, too. They make these shapes really jump out at you. And recognizing what I call shape outliers, not just extreme points, but unusual patterns in the distribution, that takes a bit more experience.
That's a great distinction. So it's not just about single weird numbers, but weird shapes. And if we miss this, we could draw totally wrong conclusions.
Absolutely.
So tying this back, how does understanding these shapes actually impact building, effective machine learning model?
Oh, it's huge. It impacts model performance right across the board. Take parametric models like your standard linear regression.
Okay.
They're very sensitive to their assumptions. One big one is normally distributed errors. And if we connect this to the bigger picture, if you plot the residuals, the errors, and you see this kind of wave-like pattern, That's a dead giveaway. The model's specified wrong. The linearity assumption is broken.
Right, so the shape of the errors tells you if the model is even appropriate.
Precisely. Then you have distance-based models. Think KANN, SVMs.
Okay.
They fundamentally rely on calculating distances between points. So imagine you have features on wildly different scales, say house price in the millions and number of bedrooms, maybe 1 to 5.
The price number is just vastly bigger.
Exactly. So the distance calculation gets completely dominated by the house price, the number of bedrooms. Almost irrelevant noise in that calculation.
So the model becomes effectively deaf to the smaller scale features, even if they're important.
That's a great way to put it. Deaf to important signals. Even tree-based models, which are generally more robust to this stuff.
Yeah, they're usually pretty hardy.
They are, but they still benefit a lot from smart pre-processing, especially if your data is really skewed or imbalanced. Good pre-processing helps them make better splits, better decisions, leads to better performance.
Okay, so it seems like no model is truly immune. Given these challenges then, what are some actionable strategies? How do we deal with this?
Right, good question. A big one is definitely how we handle outliers. But this raises an important point. Outliers aren't always errors, right?
True. Sometimes they're the most interesting points.
Exactly. Just removing them wholesale can be dangerous. You might actually stop your model from spotting critical, rare events. Think about fraud detection, Ari. The fraudulent cases are the outliers you want to find.
Okay, so just deleting them isn't the answer.
Often no. So instead of just removing them, consider how you scale your features. A really good approach here is using robust scaler.
Robust scaler. Okay, what does that do differently?
It uses the median and the interquartile range, the IQR, which is basically the spread of the middle 50% of your data.
Okay.
Because it uses median and IQR, it's way more resistant to being pulled around by those extreme values. It's probably the most resistant scaler to outliers.
So it scales things fairly, even if you have some crazy high or low values, letting the model still hear all the signals, like we said.
Precisely. It helps mitigate the impact without just throwing away potentially valuable data points.
That makes a lot of sense. So ultimately, really understanding your data's shape isn't just like step one. It feels like it's maybe the single most important thing guiding your decisions throughout the whole process.
I absolutely believe so. For you, the learner, listening right now, the key takeaway really is this.
Yeah.
The very best machine learning models, they're built on a foundation of meticulously understood and prepared data. You have to know its shape.
Know the shape.
Yeah. And here's a little provocative thought to leave you with. Next time you get a data set, before you even think about algorithms or models, just spend some real time looking closely at its shape. What hidden patterns, what biases might you uncover just by looking?
Welcome back to the deep dive. Today we've got a stack of engineering postmortems, a bunch of research papers, all asking one really expensive question.
Why do machine learning models fail?
Exactly. And we're not talking about code that just crashes. We're looking at models that seem flawless in the lab.
They get great scores, everyone's happy.
And then they just completely collapse the moment they hit the real world.
It's a massive issue.
Yeah.
And what's so fascinating across all these sources is that the failure point is, well, it's almost never the complex math.
Right. It's not the algorithm itself. It's not that the brain isn't big enough or something.
Not at all. The papers call them foundational failures.
It's the plumbing. I see this theme where beginners, they treat the ML libraries like these magic boxes.
Yeah, you just pour data in one side.
And intelligence is supposed to come out the other. But the reality is that it's this really rigorous engineering discipline.
And if you don't treat it that way, you get these failures. It all starts with data hygiene.
Okay, so let's start there. Feature scaling. It sounds so minor, almost like a formatting thing.
It does, but its mathematical impact can be, well, catastrophic.
I loved the example in the notes. You have a data set and it has age, let's say 30.
And then it has income, say $100,000.
To a person, those are just different scales, different units. But the model doesn't get that, does it?
No, it's totally blind to context. It just sees the raw numbers. And since 100,000 is just so much bigger than 30,
it thinks income is way more important.
Way more important. It basically ignores age because the other number is just louder, mathematically speaking.
So you should normalize it first, squash everything into, a standard 0 to 1 range?
Otherwise, you've baked in a bias before you've even started training.
But even with perfect scaling, you hit what the literature calls the most insidious error.
Data leakage. This one's brutal.
Why brutal?
Because your model looks incredible during testing. You get these amazing scores and then nothing. It fails in production.
Because it cheated.
It cheated. It saw the answers.
Yeah. The lone default scenario was the real aha moment for me. You're building a model to predict if someone will default.
But you accidentally leave a column in the data, something like post-default collection status.
So the model just learns that if the status is sent to collections, the person defaulted.
A perfect one-to-one correlation. It's not learning the complex patterns before the default. It's just learning the outcome. That's future knowledge.
And that future knowledge doesn't exist for a new applicant, so the model is useless.
Totally useless. And that's tied to this idea of contamination, right?
Yes. That's cleaning the data before you split it into training and testing sets.
The classic mistake. If you, say, fill in missing values using the average of the entire data set,
then your training set has now seen information from your test set. You've leaked data across the barrier.
you have to split first, then clean.
Always. Okay, so the data is clean, no leakage. We still need to know if the model is actually any good. And this is where we hit the accuracy paradox.
This is so critical. Everyone is trained to think accuracy is the goal.
The North Star metric.
But imagine you're detecting credit card fraud. Real fraud is, what, maybe 0.1% of all transactions?
A tiny fraction.
So I could build a model that just predicts no fraud every single time.
And you'd be 99.9% accurate.
And 100% useless. You didn't catch a single crime.
So for these imbalanced cases like fraud or rare disease screening,
How many of the actual positive cases did you manage to find?
you'd want high recall for cancer screening. You'd rather have a few false alarms than miss a real case.
Exactly. But there's a human bias here too, isn't there? The sources call it complexity bias.
Oh, definitely. Everyone wants to jump straight to the huge, deep neural network.
It's the shiny new toy. But the advice here is so simple. Start with a baseline. A simple logistic regression.
And if your giant complex model doesn't crush that simple baseline,
Then you probably don't need it. The complexity just adds debt and makes it a nightmare to debug.
speaking of debugging, let's touch on categorical encoding. This is such a classic pitfall.
It is. You have categories like cities, New York, LA, Chicago. You have to turn them into numbers for the model.
So you make them 1, 2, and 3.
And the model immediately thinks there's an order. It thinks Chicago, being 3, is somehow mathematically greater than New York at 1.
Which is just meaningless.
It's trying to find a trend that doesn't exist. You have to use something like one-hot encoding to stop it from hallucinating a hierarchy.
It really does feel like the whole journey from novice to expert is moving from focusing on the algorithm itself
From algorithmic novelty.
to focusing on systematic rigor, the whole system around the model.
That's the key takeaway. The code is the easy part. The discipline is everything else.
And on that note, here's a final thought for you to chew on. The sources talk a lot about proxies.
The hidden correlations.
Yeah, you think, okay, I don't want my model to use this sensitive variable, so I'll just delete the column.
But the model is an optimization machine. It will find a shortcut. If you leave in something like, say, zip code.
It can use that as a proxy to basically reconstruct the information you tried to hide.
Exactly. It finds the pattern you told it to ignore.
Which leaves us with a really tough question for your next build.
Yeah.
How do you audit a black box for biases you can't even see? Something to consider. Thanks for deep diving with us.
So, for someone listening, maybe wanting to break into one of these fields or perhaps level up, what are the ways in? How do you actually build these skills?
Right, navigating this definitely needs a bit of strategy. Your sources lay out, well, both the traditional academic routes and these increasingly important alternative ways to qualify, which is great news, especially if you're thinking about changing careers.
Let's start early then. What about high school students? How should they prepare if they're interested in this?
Yeah, building that strong academic foundation early on is just critical. The absolute core subjects are computer science, mathematics, and statistics. And it's not just about passing the classes. These subjects teach the fundamental logic, the analytical thinking that underpins everything in data science.
Which specific math topics are most important, would you say?
Linear algebra, calculus, and definitely probability and statistics. That's the theoretical bedrock. Understanding those helps you understand how the algorithms actually work later on. In computer science, getting some programming experience, especially with Python if possible, is a huge advantage. But honestly, Even a solid foundation in programming principles using another language, like Java and AP Comp Sci, is great. Python syntax is relatively easy to pick up once you have those fundamentals. And high school is also a great time to start playing with data science concepts directly. Learning about collecting data, cleaning it up, analyzing it, visualizing it, maybe trying small projects, analyzing some public data sets. Just cultivating that critical thinking and data literacy early makes a big difference.
Okay, what about university? Are degrees still the main path? And how necessary are advanced degrees like masters or PhDs?
Formal education is definitely still a primary route, yeah. And your sources strongly suggest an increasing emphasis on advanced degrees, especially for those more specialized roles or leadership positions. For a general data science role, a bachelor's in something quantitative data science, CS, math, stats, engineering is often the entry point. But as we noted earlier, the data suggests many careers, particularly the advanced ones, are increasingly asking for a master's or even a doctorate. That rise in job postings needing graduate degrees. It signals the field is maturing, and for certain competitive roles, a bachelor's might not be enough anymore. It pushes people towards higher ed for that deeper theoretical edge. For a machine learning engineer, a bachelor's in computer science, software engineering, or something similar is usually the minimum. But again, a graduate degree often provides that extra depth and project experience that can fast-track you to senior roles and better pay. It gives a competitive advantage. For a data engineer, most entry-level spots need at least a bachelor's. CS, engineering, even business with a tech focus are common. Degrees specifically in data science or analytics, with coursework in databases, data modeling, big data, highly relevant. For moving up, a master's focusing on data systems, analytics, or an MBA with an analytics track is often preferred or even required for more senior roles. For an AI engineer, given the complexity, a bachelor's in CS or data science provides the foundation. But for really understanding AI principles deeply and tackling those cutting-edge challenges, a master's or PhD in AI, ML, or a related field is highly recommended, especially for research or highly specialized roles, and for those specialized data scientists. While a quantitative bachelor's is common, many of those high-paying specialist careers increasingly require an advanced degree. Master's programs in applied data science, AML focusing on areas like computer vision or NLP or business analytics are very relevant. And it's worth noting, some master's programs are specifically designed to help people transition from non-STEM backgrounds, too.
Okay, but what if someone doesn't have that traditional academic background? Or maybe they're looking to switch careers entirely. Are there other solid options to get the needed skills?
Oh, absolutely. This is where things like industry certifications and all the online learning platforms become incredibly valuable. They offer structured, flexible, and often very accessible routes to getting specific job-ready skills. This is particularly good news for career changers or people needing to upskill effectively.
Tell me more about certifications. How much do they actually help?
They can help a lot. Industry certifications act as a clear signal to employers that you possess specific, validated skills and knowledge they're looking for. Earning a respected certification, say from AWS or Google Cloud or Microsoft Azure, can really boost your marketability because it proves hands-on competence with their platforms. For machine learning engineers, cloud provider certs focused on ML are strong options, though some require prior experience. Certs from companies like Databricks also validate skills in specific ML tools and workflows. For data engineers, again, cloud platform certifications are really popular. Microsoft Azure, Google Cloud, AWS all have them. Your sources also mention some beginner-friendly options, like a metadatabase engineer certificate or programs like IBM's data engineering certificate that are specifically designed for career changers, sometimes with no prior experience needed. For AI engineers, certifications range quite a bit. You've got introductory ones covering AI fundamentals, sometimes without even needing coding skills. Then there are more advanced ones requiring Python and diving into specific techniques or deployment practices offered by IBM, NVIDIA, and others. And for specialized data scientists, platform certs like the Azure Data Scientist Associate validate cloud skills. There are also project-based professional certificates and nano degrees on platforms like Coursera or Udacity, which are great for building a portfolio and proving you can use tools like Python and SQL effectively.
Right. And what about online courses, those MOACs? There seem to be thousands out there.
Yeah, massive open online courses, MOCs, are fantastic for flexible learning. Platforms like Coursera, EDX, DataCamp, Udacity, they offer courses and full programs, often from top universities or tech companies. For machine learning, you can find comprehensive specializations taking you from beginner concepts to advanced deep learning, usually with hands-on coding labs using Python libraries like scikit-learn, TensorFlow, PyTorch. For data science, there are tons of beginner-friendly professional certificates covering the fundamentals: SQL, visualization, data wrangling, intro ML, using tools like Python and R. Google and IBM have very popular entry-level programs. For AI engineering, you can find courses covering everything from basic AI concepts to advanced deep learning, NLP, generative AI, MLOps, often tied to specific cloud platforms or tools. And for data engineering, platforms like DataCamp and edX offer structured paths covering SQL, database concepts, Python, big data tools like Spark and Kafka, and pipeline orchestration tools like Airflow. Many include practical exercises.
That's great. Are there also good free resources people can tap into, maybe just to start exploring or go deeper on certain topics?
Absolutely, tons. YouTube is actually an incredible source of high-quality free content if you know where to look. For the crucial mathematics for data science, channels like 3 Blue 1 Brown offer amazing visual explanations of things like linear algebra or neural nets. Others provide great stats tutorials or break down the math behind specific algorithms. For ML and data science tutorials, channels like FreeCodeCamp, Data School, Data Professor offer practical guides using Python, Pandas, R. Others focus specifically on machine learning implementation. And for industry insights and advanced topics, you can find channels summarizing the latest research papers, doing deep dives into advanced tools, or featuring interviews with leading AI experts like Lex Friedman. These are fantastic for self-directed learning, staying current, and just deepening your understanding.
Okay, this has been incredibly comprehensive. So it really sounds like there isn't one single right path, but maybe different strategies work best depending on your goals and the specific role.
Exactly. That dual path seemed to emerge pretty clearly. You can aim for broad versatility, understanding and contributing across the data lifecycle, or you can choose to go deep, cultivating highly specialized expertise in one of those complex, in-demand AI subfields. Both are viable paths to success, but they might lead to different types of roles and earning potentials, especially right now with the AI boom.
And that choice between being a versatile all-rounder or a deep niche specialist.
Which really brings us to a final thought, a question for you listening. Given this rapid evolution and all these diverse paths and specializations opening up in data science, how do you decide? Which qualification method, which area of focus feels like the right one for you as you look towards your future in this data-driven world?